All right, today we are going to talk about the conservation of energy. All right, so in our lab that we did the other day and in our PhET simulation yesterday, you have actually seen the conservation of energy in play. Our lab talked about, actually said what the law of conservation of energy was, but all it is that energy can never be created, nor can it be destroyed. All right, so if we cannot create energy, or if we can't get rid of energy, then what happens? All right, so in our lab, we saw how a ball was dropped from rest. All right, so all of the energy at the beginning was gravitational potential energy, but all of that gravitational potential energy was gone as soon as it hit the ground. All right, so how can we say that energy cannot be destroyed whenever we know that GPE was gone whenever it hit the ground? So if you remember correctly, as soon as we let go of the ball, it started moving. So as soon as it started moving downward, that GPE started turning into kinetic energy. All right, so even though the GPE was gone, it was transformed into a different type of energy. And that's what happens. We did not destroy the energy. We did not get rid of it. We just changed it into a different type of energy. All right, so whenever we're talking about kinetic and potential, we talked about how that was going to be the main stuff that we were going to be using, the main types of energy that we were going to be using. All of that is under the umbrella of something called mechanical energy. All right, so you're going to see it written as TME a lot, and that's just total mechanical energy. So what mechanical energy takes into account is the amount of kinetic energy and all forms of potential energy. All right, so this Greek letter right there, that's the Greek letter sigma, and that just means the sum of. All right, so that's the sum of all of the different types of potential energy that are present. So we have two different types of potential energy that we've been talking about. It's gravitational and elastic. All right, but there are tons of other kinds of potential energy. One of the types of potential energy we talked about last year in chemistry, and that was chemical potential energy. So that's that potential energy that is stored in the bonds of compounds. All right, so we're just talking about elastic and gravitational, but there's a ton of other different potential energies as well. All right, so that sigma just means the sum of all of the potential energies. All right, so whenever we disregard air resistance, whenever we disregard friction, we can actually get more specific with the law of conservation of energy and talk about the law of conservation of mechanical energy. So that means that for a specific system, the total mechanical energy will remain constant. All right, so the amount of GPE might not stay constant. The amount of KE might not stay constant, but the total amount of mechanical energy will be constant. All right, so you actually gave me this equation in your lab on Monday. Or the other day, excuse me. All right, so you gave me that equation in your lab. You were told that the sum of all of the initial energies that you started with equal the sum of all of the energies that you end with. All right, so we just had gravity working on that ball whenever we dropped it the other day. So we could get more specific with this and make this GPE initial and GPE final. So we can break that down even further into 1/2 mv initial squared plus mgh initial, because the mass isn't going to change of the object. All right, if our kinetic energy changes, it's just going to be due to a velocity change. If our GPE changes, it's just going to be due to a height change. All right, so we can break it down into this new equation. All right, so let's take this new equation that we have right here, and we are told that an object that is held at rest at some initial height is dropped and allowed to impact the ground. We want to rearrange this equation to solve for the final velocity of the object that split second before it hits the ground. All right, so we want to rearrange this equation to solve for V final. All right, well, that can look a little bit intimidating. So let's think about some things first. All right, so it is held at rest. Well, if it's held at rest, then we know our V initial is going to be 0. So if our V initial is 0, that means our entire initial kinetic energy is 0. And then if it's allowed to impact the ground is our 0 level. So our final height is also going to be 0. Well, if our final height is 0, that means our final potential energy is also 0. So that makes it a little bit more manageable. All right, so we have mgh initial is equal to 1/2 mv final squared. So we're still trying to get V final by itself. All right, so remember, we're going to work our way out in. So the first thing that we want to get rid of is that 1/2. So in order to get rid of the 1/2, we multiply both sides by 2. Okay. After that, we want to get rid of the mass. So we're going to divide both sides by m. Now, that gets rid of the mass on this side because we have a mass on top and a mass on bottom. But look at the other side. We also have a mass on top and a mass on bottom, which is going to cancel out over here. So that tells us that our final velocity does not depend on our mass. So it just depends on two different things, and that's our acceleration due to gravity and the height that we fell at, or the object that it was at in the beginning. All right, now we're not done yet. The last thing that we have to get rid of is this square, and we're going to take the square root of both sides. All right, so let me make that a little bit cleaner over here. So we have V final is equal to the square root of 2GH initial. All right, so if you want to memorize this equation, you're more than welcome to. But the thing that you have to remember is that you can only use it whenever you have an initial kinetic energy of 0 and a final potential energy of 0. That's the only time this works. All right. So in our lab the other day, we saw that the ball did not bounce back up to its original position. So you were asked, so that tells us that some of the energy was lost. And you were asked to give examples of why that energy was lost. All right, so a lot of people said air resistance, which is fantastic. Air resistance is a type of friction. It's a fluid friction. So yes, it absolutely does dissipate energy. That's what we're going to see in just a second. Some people said that energy was lost on the bounce. Absolutely. And then others said that gravity was a reason why it didn't bounce as high as it did. And that is absolutely wrong, and this is why. All right, so gravity is something called a conservative force. So gravity does not dissipate energy. That means it does not get rid of energy out of that system. So if we look at this cliff diver, all right, this diver had to walk up this cliff in order to get to the top. Well, we learned in our first set of notes for this unit that if you were to input work into a system, that's going to change the amount of energy in that system. So, of course, this person is inputting work, But gravity is also doing work as he goes up. So gravity is doing negative work as this kid goes up the cliff. All right, but yes, he is inputting work. Gravity is doing work, but he started down here and he is climbing up the cliff. So what he is doing is changing his energy. So all of that work that is going in is changing his energy to make all of the energy up here GPE. All right, well, as soon as he jumps off of the cliff, that GPE is being turned into kinetic energy. All right, so gravity is once again doing work. It's doing positive work as he pulls it down. All right, so that gravity is being recovered, or that work is being recovered as that kinetic energy, or as that GPE is being turned into kinetic energy. So we don't have any energy lost, we just have it being transformed. Friction, on the other hand, is a non-conservative force. That means that it is going to disperse energy, or it is going to dissipate energy to the surroundings. All right, so what you see right here, we have a race car that's got that metal scraping the pavement. All right, so you see this big ball of sparks right here. All right, that's like baby fire. So we have heat being given off. This is called thermal energy. All right, and that should make sense, because if you were to rub your hands together, that is going to make your hands warm, which is a type of heat. That friction, you're inputting work, moving your hands against each other, and that friction is giving off that energy as thermal energy, as heat. And if you were sitting in the crowd right here, you would also hear this awful screeching sound, which is sound energy. All right, so that friction is not only giving off thermal energy, but it is also giving off sound energy. All right, so what do you think would happen to the kinetic energy as that friction is getting rid of that energy slowly but surely? All right, hopefully you're saying that the kinetic energy will decrease. It's going to slow down until it comes to a complete stop. All right, so here, this is an animation. If you do go to the PowerPoint, you can actually turn it on to a PowerPoint and see this animation. But at this point right here, all of your energy is going to be GPE. So that's what we're seeing here. All right, so it's all GPE. So as it goes down, that GPE is slowly turning into kinetic energy. So right here, you have both GPE and kinetic energy. All right, so you would see kinetic energy kind of go up, and this would go down at the same time. But all the while, this total mechanical energy would remain constant. So that green would be the same the entire time. Now, right here, all of that kinetic energy turns into, all of that GPE that it started with up here turns into kinetic energy. Now, what do we have here? We have unpacked snow. All right, so that unpacked snow is going to increase the amount of friction. So whenever you watch this animation, you'll see that as soon as it hits that unpacked snow, negative work begins to happen. And as this negative work begins to happen, this kinetic energy is going to go down, and so will the total mechanical energy. All right, so if you ever have friction, you do have a loss of both kinetic energy and mechanical energy. All right, so it's going to eventually slow down and come to a stop. All right, so we have our first example. So we have a child who starts from rest, zooms down a frictionless slide from an initial height of 3 meters. What is her speed at the bottom of the slide, assuming she has a mass of 25 kilograms? All right, so let's write down our givens. All right, so the first big given was starting from rest. That should tell us that we have an initial velocity of 0. All right, the frictionless, even though that's not one of our givens, that means that our energy is going to be conserved. All right, so that's going to play a big part in it. So because it is frictionless, no energy is going to be lost. So energy is conserved. All right, we have our initial height of 3 meters. That was given. We're looking for her speed at the bottom of the slide. So we are looking for V final. Now, something else that is not necessarily a numerical given, but we do have to realize it, is that we are looking for her speed at the bottom of the slide. So the bottom means that our final height is going to be 0. And the last thing that we are given is the mass of 25 kilograms. All right, so we know that energy is conserved, so we can use our conservation of energy equation. So we have GPE initial plus KE initial is equal to GPE final plus KE final. Well, let's break that down even further. So we have MGH initial plus 1/2 MV initial squared is equal to MGH final plus 1/2 MV final squared. Now, there are a couple of things that we need to realize. Our initial velocity was 0. So if our initial velocity is 0, that makes this whole thing 0. If our final height is 0, that means that this is 0. So that means this whole thing is also 0. All right, so we have MGH initial is equal to 1/2 MV final squared. So again, solving for V final, the first thing that we're going to get rid of is that 1/2. So we're going to multiply both sides by 2. That gets rid of that. Then to get rid of the mass, we're going to divide both sides by M. That gets rid of mass on this side and mass on that side. So even though we were given the mass, we did not necessarily need it. And then last but not least, we do have to get rid of that square. So we're going to take the square root of both sides. So V final is equal to the square root of 2GH initial. So we plug that in, we get 2 times 9.81 times our initial height of 3 meters. You should get an answer, let me look, not there, of 7.67. That's our numerical value. Now, we do have the unit for velocity is meters per second, and we know that velocity is a vector quantity. This child was sliding down, so our direction would be negative. So the final velocity of the child is negative 7.67 meters per second. Okay. Next example, we have a 50-kilogram gorilla is sitting on the limb of a tree 4 meters above the ground. All right, we want to find the gravitational potential energy of that gorilla sitting in the tree. So we're looking for GPE. All right, so we know that GPE is equal to MGH. We have mass, we have height, and we know G, so we can just plug it in. So we have 50 times 9.81 times 4 does give us a value of 1,962 joules. So as that gorilla sits in that limb 4 meters above the ground, it has 1,962 joules of gravitational potential energy. Now, it jumps down from the tree to the ground. All right, we want to know what the velocity of the gorilla was just before hitting the ground. So we have to use our conservation of energy equation. So once again, we know that GPE initial plus KE initial is equal to GPE final plus KE final. So let's break that down. MGH initial plus 1/2 MV initial squared is equal to MGH final plus 1/2 MV final squared. Once again, she started from rest. All right, so our initial velocity is 0. So there was no initial kinetic energy. And then the gorilla jumped down to the ground, so our final height was also 0. So that makes our final potential energy 0. So again, we have MGH initial is equal to 1/2 MV final squared. Solving for V final, we do get the square root of 2G times the initial height. So we plug that in, we get the square root of 2 times 9.81 times 4. And we do get a velocity of negative 8.86 meters per second. The negative is because the gorilla was jumping down. And then last but not least, the gorilla, feeling exuberant, throws a 0.140 kilogram banana straight up into the air from the ground with an initial energy of 20 joules. How high will the banana go? Well, we're looking for the height. We know the mass of it is 0.140 kilograms. All right, well, that looks like the making of GPE. So we know that GPE is equal to MGH. All right, so we're looking for H. We know M, we know G, but we need to figure out what GPE is. So we're told that the initial energy that was put into it was 20 joules. Now, all of that energy, it was on the ground, it was kinetic energy. But as that banana rose to that height that we're trying to find, it slowly turned into GPE until it reached that final height where all of it turned into GPE. So we can assume that our GPE is 20 joules. All right, so once again, solving for height, we have to divide both sides by mg to get rid of those. So height is equal to GPE over mg. All right, so we have 20 joules over our mass of 0.140 times 9.81. All right, we do get a height of 14.6 meters. All right, so that banana will go to a height of 14.6 meters. All right. So now we're going to look at another example. This is going to be Hawkeye. All right, so any Marvel fans out there, Hawkeye does use a bow and arrow. All right, so we should know, like, we have to pull the bowstring back, and whenever we pull that bowstring back, we are inputting work, which is changing the amount of energy. We are stretching that string from its resting position to a new position, which is storing elastic potential energy. All right, so we know that this bow has a constant of 1,100 newtons per meter. All right, so we know that constant that is measured in newtons per meter is our K. All right, that's our spring constant. He loads the bow with an arrow that has a mass of 0.5 kilograms, and he draws the bowstring back 0.85 meters. That 0.85 meters is the distance that it was stretched from its original or resting position. So that's going to be our X. So the first thing asks, how much energy does the bow store when it is drawn back? All right, so we've already talked about it. The type of energy that it will store is EPE. So that's what we're looking for. Our equation is 1/2 kx squared. All right, so we plug that in. We have both of those. So we have 1/2 times 1,100 times 0.85 squared. So the first thing that you need to know, we have to use order of operations. So we're going to have to do this first. So that's going to give us 1/2 of 1,100 times I think it's like 7,225, maybe. All right, and then let me get my calculator. And then we multiply that. That is going to give us 397.4 joules of elastic potential energy. All right, so the total amount of potential energy stored in the bow is 397.4 joules. The second question asks how much of that energy is given to the arrow. All right, so as soon as that bowstring is back to its original position, all of the energy is going to be transferred to the arrow itself. All right, so he shoots the arrow straight up into the air. We want to know, again, how high will it travel? So we're looking for the height. All right, we know the mass of this arrow is 0.50 kilograms. We obviously know G is 9.81. And we know that all of the energy at the very top of its path is GPE. So if all of this energy was transferred to the arrow at the top of the path, all of that energy is going to be GPE as well. So our GPE is 397.4 joules. So we know that GPE is equal to mgh. Once again, solving for h, we divide both sides by mg. H is equal to GPE over mg. So we have 397.4 divided by 0.50 times 9.81. Let's see what we get. So we get 397.4 divided by 0.5 times 9.81. We do get 81.02 meters. So this arrow went 81.02 meters in the air. All right, so that brings us to this pendulum. These are going to be the last two things that we do. All right, so we're going to be really focusing on pendulums later on whenever we talk about something called simple harmonic motion. But I really want you to see something here. All right, so this pendulum is going to swing back and forth. All right, so this is its highest point, which means it's going to stop moving for that split second. So it's going to have no motion for that split second. So there's not going to be any kinetic energy at that highest point. So all of the energy is going to be potential. Now, as it travels downward, that potential is turning into kinetic. So at this point, you have a little bit of potential and a little bit of kinetic. But whenever it gets down here, once it gets to its resting position, all of it will be kinetic. It will all be kinetic. And this is where, if you were to play this animation on the slides, you'll see that it has its highest velocity at this point. All right, so once it passes through that equilibrium position, though, it's going to be affected by gravity, so it's going to start slowing down. All right, so right here, we've got a little bit of kinetic and a little GPE. And again, at the very top, it's going to be all GPE. So over here, these two places, these are its maximum displacement where it's all GPE. Down here, that's at its resting position where it's all kinetic energy. So at these places, it has the least amount of velocity. It stopped. Right here, it has the most velocity. All right, so we're going to fill in this chart below. So we have this pendulum right here. It's swinging from A to B to C to D to E. Now, we have a 2 kilogram mass, and we're going to find out how much potential energy, kinetic energy, what its velocity is, and its total mechanical energy is at each and every one of these points. Now, somebody will ask, well, why isn't E on here? Well, what you need to notice about A and E is that they are at the exact same position. All right, so this would be right here. All right, so these are the maximum displacement away from the equilibrium position. So at those two positions, at A and E, it stops for that split second, so our velocity is 0. If we have 0 velocity, that means that our kinetic energy is also 0. So that means that all of the energy is potential. So in order for us to solve for that potential energy, we need to remember our equation, which is mgh. Well, the mass is 2. We know g is 9.81. And for this, our height is 2. So we have 2 times 9.81 times 2, which does give us a grand total of 39.24 joules of potential energy. 39.24 joules of potential energy. Now, this is our total mechanical energy. Remember that mechanical energy is equal to kinetic plus potential. So 39.24 plus 0 is equal to 39.24. Now, in this situation, we are considering it to be frictionless. So that means that the total mechanical energy is conserved. So all of these will be 39.24. That will be constant. All right, so look at B. All right, so B is not at the highest point, but it's not at the lowest point. So we have a little bit of potential and we have a little bit of kinetic. So which one do you think would be easier to find first? Hopefully you're saying potential. All right, so we don't have the velocity yet, which is why we can't use kinetic energy. So remember, kinetic energy is 1/2 mv squared. We have the mass, we just don't have the velocity. All right, so we solve for the potential energy, 2 times 9.81 times this 0.8 meters. We do get a potential energy of 15.70 joules of potential energy. Now, how do we find the amount of kinetic energy? We just subtract 15.7 from 39.24, which is going to give us 23.54. Now that we have our kinetic energy, we can solve for our velocity. So remember, to solve for velocity, that is the square root of 2 times the kinetic energy over the mass. So we plug in 2 times 23.54, divide that by 2, and then take the square root of that. We do get 4.85 meters per second for that velocity. Now look at C. C is at ground level. So at ground level, we know that our final height is 0. So our potential energy is 0, which means all of the energy is kinetic. So all 39.24 joules of energy is kinetic. So once again, we plug in that kinetic energy to our velocity equation. So 2 times 39.24 divided by 2, take the square root of that. We do get 6.26 meters per second as our velocity. Now, look at D. D, again, has a little bit of potential and a little bit of kinetic. So let's solve for the potential first. We put in 2 times 9.81 times 1. We do get 19.62. Well, if we subtract 19.62 from 39.24, we get 19.62. I wonder why that is. All right, if you notice, it doesn't look like it. It's kind of a misrepresentation right here. But this distance is exactly halfway between the lowest point and the highest point. So there's just as much potential as there is kinetic at that point. All right, so we can find our velocity once again by plugging it into this equation to get 4.43 meters per second. Now, one thing that I want you to notice, our velocity is the highest at the equilibrium position at C. It gets a little bit lower, so 0.8 is closer to the ground than this one is. So this is a little bit higher than this is. So the closer you get to the equilibrium position, the faster you're going to be. All right, so once again, A and E, those are our maximum potential energy. C is maximum kinetic. So where there's maximum kinetic, there's going to be minimum potential. So C is also the minimum potential, whereas A and E are minimum kinetic. And then right here at D is where kinetic and potential are the same. They're equal to each other. All right, so that's it for conservation of energy. We're going to do a little bit of practice next, but if you are still having trouble, please ask me some questions. That's why I'm here.